Okay, so you need your worksheet, the guided notes. We're going to go through those today, right now. We're going to first do some vocabulary words. So, vocabulary words that we need to look at are, I'm going to have to sneak over everybody's, that's okay. Potential energy, and kinetic energy. These are the first two. Potential. Whenever you think about potential, what do you think about? Give me a definition. Possibility, okay. Give me more words. Okay, stored up. Whoops, that was lovely. Okay, what else? Another word for potential. Chance, okay. This all has to do with energy. So I've got energy stored, or I've got a chance of having a lot of energy, like a ball at the top of the hill. It has a potential to have roll down the hill, right? Or if I wanted to be a doctor, I have a potential to be a doctor. It's my choices from forward going now with education, if I am able to do that or not. Okay, so potential is stored up. Chance, I said off. That was good. Of, you guys, anytime I make a mistake, make sure you're correcting me. Okay, all right, kinetic. Okay, moving. Okay, what else? Movement. What else? Motion. I'm using it right now. It's anything that I can see, right? Anything that I can see or feel. Okay, so potential energy is the chance of doing something, but kinetic energy is what's actually happening, the motion of doing something. It's the doing part. Okay, then we have what unit represents energy, right? Does anybody know? It's what? Got it, whatever. It's a joule, which is represented by a J. And we'll go into that a little bit more later. Just know that it's a joule. In the English system, you would probably know it as a calorie. And when you think of calories in food, it's actually a kilocalorie. So you're actually thinking a kilocal for food. But they call it a calorie. And they usually write it with a capital C for that, for calorie. But in the SI unit, which is System International, which is metric, we use a joule. So joule is our standard that we're going to be looking at. So not this. This is Old English, right? Okay. So now in the next section, you have an area that tells you some things that energy can appear: temperature, sound, light, electric, chemical, nuclear, and elastic. I am going to show you some things now, and you're going to tell me if it's kinetic, if it's energy of motion, or if it's potential. Okay, this is one of these little wind-up cars, you know, that you pull back and then you let go, and this one didn't work. Try it again. Okay, that one didn't want to work. I must have busted it. Okay, pull it back. Oh, come on, really? And it goes. There we go. All right, so if I pull it back and I hold it here, what kind of energy? Potential. When I let it go, kinetic, because it has motion. So as we're doing these examples, I want you to put examples down under which one you think it would go on. So which one would this little car fit under? Elastic, yeah. Have you ever seen one of those airplanes? I looked all over at the store for the airplane that you have the elastic and you wind it up and then you let it go. I looked all over for that. I could not find them. Yeah, the balsa wood one. Okay, I know now where to get them. Okay, so this is just an elastic inside that has been wound up, and then I let it go. So tell when it was potential and when it was kinetic. So write this on your notes underneath elastic. This is my favorite one. Okay, this is, for those of you that are watching this, an air horn. It's loud. It's actually got chemicals in it that help us with that. Okay, so air horn. As it is right now, it's potential, but the minute I push it down, wow, that didn't want to come back up. I thought, well, no, we're going to be stuck with that sound all the time. Once I push it down, it becomes kinetic. Which one does this one fall under? Sound. Okay, so before it's potential, it's just sitting there, it's not doing anything, but it has the potential to make sound. Then the action of actually doing helps me know when what will go on. Okay, so here I have batteries. Which one's this one going to go under? Electric. Okay, so this is electric. You might change your mind on which ones it'll go under in just a second. I've got it hooked to a Christmas light. One thing to do with bad Christmas lights, cut them apart and do this. Okay. If I connect the circuit, and physics goes over this and engineering goes over this, I get light. Okay, so tell me what just happened. What are we going to put under what? Okay, light and waves will give me kinetic or potential. Right. What about the battery? What about the battery? It was potential before I did anything, right? But once I started using it, even though I can't see it, it becomes kinetic. So once I start using a battery, it becomes kinetic. Now, if you don't want to put this light one down, how else do you use batteries? Cell phones, cars, remote controls, your clickers. Okay, there's lots of different ways we can use it. Okay? All right, now, we have a couple areas that we haven't touched, right? Actually, we've got one more that I'm going to show you. This one. We're actually going to use this in a lab later. Okay, tell me about these. Okay, these ones actually, when you undo them, then they'll warm up because they're kept in an oxygen-free environment. So when I add oxygen to it, then the reaction starts. What state are they in? When and when? Potential before it's open. Kinetic after, and it is chemical, yes. Okay, so now I want you to take 5 minutes. I'm going to pause the video, and I want you to pair share, come up with as many different ideas under each of these as you can possibly get. And then I'm going to have you share your most, you think, amazing one that you found between the two of you. So 2 minutes, pair share. Actually, 2 minutes pair share because we're a little bit slow. Okay, so time's up. What did you come up with? Okay, Jade. A bullet. Okay, so. Okay, and then after it would be kinetic, right? Okay. All right, let's go just in groups here. What's yours? Light switch for electric. Okay, so before potential, turn it on. Kinetic. Okay. Give me one. Temperature match before it has potential. Strike it. And then you've got light and heat, right? Good. Okay. Boiling water. Okay. So before it has a temperature to boil, after we put heat into it. Okay. All right. Okay, the snaps. Okay, so before they're just paper, and then you throw them and it hits something and you hear the snap and you have a little light explosion. Good. Did you have any?
For temperature, rubbing your hands together.
Rubbing your hands together. So before, nothing, but when you rub your hands together, you get friction and warmth. Okay. Flashlight. So before, nothing. Turn it on, you got light.
The obvious one nuclear would be the A-bomb.
Okay, the A-bomb. Before, nothing. After, nothing. Okay. Sorry. Okay. Oh, we got all the way back to the beginning. Okay. So the other one that you probably didn't think about for nuclear would be like X-rays. Okay, the X-ray machine can just sit there and does nothing until it's turned on, and then the X-rays come. Another one would be a nuclear reactor. So to produce energy, nothing happens when the control rods are in. They lift the control rods, and we got a nuclear reaction that will give us heat and circulate. Okay, is there any area that you don't have anything in? You need to have a couple examples down in each of those areas. Now remember, as we were looking at light, if we remember back from what we had just basically, we talked about waves in light. So if we had a jump rope, like when you're back in elementary, and we did the snake and we did a slow wave, it doesn't take much energy, and the wavelength is pretty long, okay? If we did a lot of energy, and I'm not going to be able to do that, but the waves would get shorter and closer together. Which one took more energy? The shorter one. You had to really move fast to get the shorter wavelengths, and you were doing jump rope. Okay, so let's go on. Temperature is important in thermochemistry. That's one of the things, one of the ways we measure that something's happened. So we talk about Kelvin. Can anybody tell me about Kelvin? Anybody know anything about Kelvin? Can be hot, can be cold. What's special about the Kelvin scale? I already have the Celsius scale. I already have the Fahrenheit scale. Why do I need this Kelvin scale?
Designed so that when it hits zero, that's absolute zero.
Good. When it hits zero, it's absolute zero. So we call it the absolute scale. In other words, there are no zeros. We've never reached absolute zero. We've come close, but we've never made it there. There are no negatives. So what? Well, the so what is when we have equations and we have temperature on the bottom of the equation, something divided by temperature. If I divide that something by zero, what happens to my number? It's undefined. I can't divide a number by zero. If I have a negative on the bottom and what I'm solving for is mass, then I end up with a negative mass. That's sort of hard to get. Okay, so I want to have a positive number for temperature so that I can actually get numbers that count and make sense for other things. And as we go into other units, you'll see how this really is important. So it's an absolute scale. The divisions are the same as the Celsius scale. They're the exact same. The only difference is Celsius goes negative, but Kelvin does not in our realm of things right now. Okay, so how do I get from Celsius to Kelvin? Well, Kelvin is equal to Celsius plus 273.15. You'll notice I did not put a degree sign with the Kelvin. Kelvin does not have a degree sign. Okay? So, we also need to know how to convert between Celsius and Fahrenheit. Now, does anybody know what this number is in Fahrenheit? Okay, does anybody know what this number is in Celsius? What does it represent? They're both boiling points of water. Okay, they're both boiling points of water. So it's a lot easier. The Celsius scale is based on the boiling point and the freezing point of water. The Fahrenheit scale, I don't know what it's based on. 212 for boiling point, 32 degrees for freezing of water. They don't make any, there's no correlation. Okay, so the Celsius scale is a little bit more precise. So to get from, say that we wanted to go from Fahrenheit to Celsius, we would take degrees Fahrenheit and we would subtract 32, and then we would divide it by 1.8. Now remember, this has got to be done first before you divide it by 1.8. If I wanted for some reason to take a Celsius temperature and convert it to Fahrenheit, I would do it this way. Okay, so those are two equations that you might want to know. Now, instead of using 1.8, sometimes they use 9/5 or 5/9, but 1.8 will work. Okay, we're in a digital anyway. Okay, so the next thing that you have on your guided notes is this symbol. Does anybody know what that means? Does anybody know what this means in math? A triangle. Yay! Okay, what else? A triangle? Yes? Could be an angle. Nobody's. This is a capital delta. Okay, a small delta looks like this. That means change. Okay, so when they have a delta, it means change. This one is a small symbol for change. That's a large symbol for change. So this is just like a slight change. This is a big change. And of course, T is going to be temperature. Just the change in temperature. That's it. That's what that means. Okay? So as we're looking at that, we are going to be using that in some equations. So we want to know what the change in temperature is. Okay? Last couple things I want to go over on that first page is endo and exothermic. And you'll see me shortcut reactions with RxN a lot, just because I don't like to write reaction all the way out. And if you've ever gone to the pharmacy, they often do that. That just means it's the reaction. Okay? So you'll sometimes see me shortcut it that way. Okay, so when we look at this, if we take thermic has to do with heat, right? And I missed the M on that one, sorry. Thermic, this is heat. Writing on the board, you lose spelling sometimes. So as I look at this, this is endo, this is exo. What does that mean to you? Exo means exiting, so heat is leaving, right? Is delta T going to be positive or negative? Okay, for the surroundings, it's going to be positive because that reaction is giving off heat to the surroundings. If I was looking at the object itself, it would be negative because it would give off heat. So we're going to say positive because we're going to be filling this, just like the heat warmer, or the hand warmer. We're going to activate it. It's actually losing heat to us. But we're the surroundings, we're going to gather the heat. So this delta T, we're going to call with the surroundings, because that's usually what we are measuring. Okay? All right, let's look at endo. So exo and endo. Endo means in. I'm taking in heat. This would be like the cold packs. If you've ever played sports and you need to have one of those instant cold packs. Okay, basically that is two chemicals separated by a small film of plastic. So when you break that film of plastic, the two chemicals are able to mix. And because they mix, you start feeling cold because the reaction is taking heat from you into the reaction. So it feels cold to the touch because it takes heat away from you. So heat is taken in to the reaction. And delta T for this is going to be what? For the surroundings. It is going to be negative for the surroundings. Now, as we look at this, endothermic, that is going to go heat on the reactant side of a reaction. So where would the exothermic heat be? Products, yep, given off. Okay. Don't lose this. We're going to keep using this over the next couple of days. We're going to do a quick exit quiz. So hopefully you're still signed in. Did everybody get this down? I'm going